Howdy folks, this is Mr. Ryan, and in calculus today we are going to discuss the topic optimization. Now as you can see, I have written here optimization 1. That's because we are going to spend more than one day on the subject of optimization. It's a very important topic within the subject of calculus. Now what I've put on the board here, we're going to discuss at first, is one of the important theorems of calculus, which is called the extreme value theorem. Now, this is the extreme value theorem written out, but a lot of times it's easier to understand the extreme value theorem when you look at a graph. It's a little bit easier to understand. So let's read the extreme value theorem here. It says that any function, that means any function in the universe, okay? Any function that is continuous has to be continuous, so that is our first premise, is that the function is continuous. Any function that is continuous on the closed interval from a to b. So that's the second premise, that it has to be on a closed interval, and this a and b, those are x values. So the fact that they're brackets, that means that it is a closed interval, so this interval includes a and it includes b. So any function that's continuous on a closed interval will, absolutely will, here is our conclusion. Got our two premises, and then here's our conclusion, will have an absolute minimum and an absolute maximum, okay? And when I say absolute minimum, absolute maximum, I mean a highest value and a lowest value. And we'll look at the graph over here and we'll talk about some of the things that that means, okay? So if we look at this graph over here, let's say that this curve represents the graph of the function f of x, okay? So that is the graph of the function f of x. And here we have an x value, which we're going to call a, and here's another x value that we're going to call b. And you can see that this graph is just a piece of a function, and it starts at a, and it continues all the way to b. Now you can see that there are no holes on the function. There are no vertical asymptotes. There are no jump discontinuities. So we have no discontinuities at all. Therefore, the function is continuous. And because we have closed circles, closed points at the end points, that means that it's a closed interval that includes a and b. And so this function on this interval will have an absolute maximum, a highest point, and an absolute minimum, a lowest point. And you can actually see them. That looks like the highest point right there, and down here that looks like the lowest point, right? They also happen to be relative that's a relative maximum and a relative minimum. It's very common for the absolute maximum to also be at a relative maximum. Very common for the absolute minimum to also be at a relative minimum, okay? So this is sort of a very common or typical situation, but I'm going to erase this and I'm going to put another situation up here that could potentially occur. All right, look what we have here. This is another function. We'll call this one, let's say, g of x. This is function g of x, okay? All right, you can see that from a all the way over to b, no discontinuities, right? It includes closed circle at the end here, closed circle at the end here. It includes a and b, okay? And so what we're going to say is, by the extreme value theorem, this piece of this function between a and b must include an absolute maximum and an absolute minimum. Only in this case, the absolute maximum is at the end point, and the absolute minimum is also at the other end point, okay? So it's okay on the interval for the maximum and the minimum to be at the endpoints. That's okay, and that happens a lot. When we do some problems later where we're trying to identify the maximum and minimum, one of the things you have to understand is we always check the endpoints to see if that's where the maximum or the minimum are, okay? So this is another possible situation that you'll face. Let's look at another possible situation. All right, here's another curve right here. And as you can see, it's continuous, starting at A, going all the way to B. A and B are included. We have closed circles at the ends of the endpoints of this piece of a curve. And now what you'll see is that the highest point between A and B is up here. So the absolute maximum is in between. But the absolute minimum is over here at the end point. And so it's okay for one of your extrema, that's what we call them, extrema. It's okay for your absolute maximum to be in the middle and for your absolute minimum to be on one of the ends. It's also okay for your absolute minimum to be in the middle and for your absolute maximum to be at one of the ends. I mean, we could very easily draw that situation. We could draw, let's see, here's A, and then the graph does this. And now in this particular case, you can see that the minimum is on the interim, somewhere in the middle, and the absolute maximum is at the end. Now we're going to look at some kind of weirder situations. All right, look at this one here. This one looks kind of hilly, right, with a valley right there in the middle. It's sort of apparent. Well, first let's say we're continuous from A to B. A and B are included. Looks to me like the lowest point is over here at B, so the absolute minimum is at an endpoint. But look at the absolute maximums. It appears to me that the absolute maximum actually shows up in two places. That this point right here at the maximum there is just as high as this maximum here. Now that's going to happen on the, for example, the sine function or the cosine function, where the sine function, it goes up to 1, then it comes down to -1. Then it goes up to 1, then it comes down to -1. Then it goes up to 1, and then down to -1, and onward to infinity. That's okay. It is okay for the maximum value to occur more than one time. That value is still the maximum value on the interval. You might be thinking to yourself, well, if that maximum value occurs twice, then there's two maximums. No, it is the maximum height because the height is equal. And let's call this, let's call this point C, and we'll call this point D. X equals C and X equals D. We can say that f of C is the same as f of D. They're equal. And so it's okay to have the same maximum occur multiple times. Similarly, you can have the same minimum occur multiple times. Now let's look at one more situation where the extreme value theorem can be applied, but it's a little strange. All right, here's what we have. We have a constant function where the function itself is constant. It's flat. And so from A to B, the function is continuous. A and B are included. We have closed circles, so the extreme value theorem can be applied. So therefore, there must be an absolute maximum and an absolute minimum. But here's what you're going to say. You're going to say, yeah, but it's a constant value, so all the values are the same. Well, the extreme value theorem doesn't say that the absolute maximum and the absolute minimum have to be different numbers. The absolute maximum and the absolute minimum can be the same number. And so it's important that you understand that. And how many times is that maximum and minimum occurring? Well, it's occurring an infinite number of times. Okay? So even with a constant function, we are still guaranteed an absolute maximum and an absolute minimum. Now I'd like to look at a few situations where the extreme value theorem fails. Okay, in this situation, you can see that the function appears to be continuous on the entire interim. However, the point at x equals a, that's included, but the point at b is not included. This is not a closed interval. We're going from a up to b, but on the b end, it's an open interval. And therefore, the extreme value theorem cannot be applied at all. You can't apply the extreme value theorem at all. However, interestingly, we still actually have an absolute maximum and an absolute minimum. The absolute minimum is at the end point that includes A, and the absolute maximum is in the middle. Here's the point that I want to make by this example, is that just because the extreme value theorem cannot be applied doesn't mean that there is no absolute maximum and no absolute minimum. Here's what I mean by that. There are many people who believe that if the premises are not fulfilled, they believe then that the opposite of the conclusion is true, and that's just not the case. There is no theorem that guarantees that there is no absolute minimum and no absolute maximum if the function is not continuous or not on a closed interval. So you can't do the opposite of the extreme value theorem. The only thing that happens is if the function is not continuous on the interval, or if it's not on a closed interval, all you can simply say is the extreme value theorem cannot be applied, and we cannot guarantee that there is an absolute maximum or an absolute minimum. Let me show you a situation where there would not be an absolute maximum or an absolute minimum. All right, this is basically the same situation, only now on the B end, the graph goes a little bit lower. So here, it's an open interval, so we can't apply the extreme value theorem. However, there is an absolute maximum, but there is no absolute minimum. There's an open circle at what would be the lowest point. And what that means is that this graph is getting ever infinitely closer to what would be that point, but never actually reaching it. Therefore, there is no absolute minimum. The graph can never actually reach that because there are an infinite number of values between this point and what would be the point where B is. Okay, so this is an example of no absolute minimum, but we do have an absolute maximum. Let's say, on the other hand, that there was an open circle where there would be a maximum. Now the function is not continuous. It has a hole. So it's not continuous, and it's not on a closed interval. We definitely cannot apply the extreme value theorem. Additionally, if we look at this, we can see that there is no maximum because from either side, the graph is trying to reach a higher and higher and higher point. And because it can keep trying to reach a higher and higher point, but never actually reaches a maximum point, there is no maximum. Okay? And so this is the idea that we're going to look at when we try to identify the maximum and minimum. If we can apply the extreme value theorem, then we know we will find a maximum and a minimum. But if we cannot apply the extreme value theorem, then we have to be cautious, careful as to whether we will find a maximum or a minimum point. So now what we're going to do next is I'm going to give you a procedure on how to identify the absolute maximum and the absolute minimum of a function on an interval. All right, let's let the rubber hit the road here. Let's go ahead and do an optimization problem. We're actually only going to do sort of the second half of an optimization problem, and then when we do the second day of optimization, we'll move backwards and do kind of what I consider to be the hardest part of optimization. The easiest part of the optimization is when you already have a function and you're just trying to find the maximum and minimum. So this problem says identify the absolute maximum and the absolute minimum value for this function f of x on the closed interval from 0 to 6. Now, this function is polynomial. Therefore, it is continuous. From negative infinity to positive infinity, continuous. Because all polynomials are continuous. And it's on the interval, the closed interval from 0 to 6. Since it's a closed interval, the extreme value theorem applies. There must be an absolute maximum and an absolute minimum on the interval from 0 to 6 on this function f of x. And what I've done over here is I have written down, if you want to pause the video and copy that down, this is the procedure that we are going to follow to be able to identify the absolute maximum and the absolute minimum. It's a pretty easy procedure. So let's go ahead and do it. Let me grab a marker here. All right, step 1 says identify all x value candidates for maximum and minimum. Here's what that means. There could be 30 or 40 or 100, usually only a few, but there could be several possibilities for maximum and minimum. Because the maximum and minimum points are indicated by certain very specific points on a function, those qualities could show up several times. So we want to make a list of all the possible candidates, all the numbers that could possibly be the maximum or the minimum. Now, there's two types of candidates for maximum and minimum. First of all, the endpoints. We said that in the last video on extreme value theorem. These endpoints, 0 and 6, Those are possible candidates. So that's 2. Now let's see where the rest of the candidates are going to come from. The other candidates for maximum and minimum are the critical values on this interval. So the critical values of the function on the interval from 0 to 6. Now, if you don't remember what critical values are, you're going to want to write this down. Remember that a critical value is the 0 of the derivative. That's the most basic definition. Technically, it's the zeros of the derivative and any points of discontinuity. But remember that this is a continuous function. Therefore, there are no points of discontinuity. So in this case, all of our critical values are simply going to be the zeros of the derivative. Okay? So how are we going to find those critical values? Well, we're going to set the derivative equal to 0, and then we're going to identify the zeros on the interval. Now, you may have to use a graphing calculator to be able to do this. So I happen to have one right here. And you may also want to get a graphing calculator out so you can identify the zeros of the derivative. All right, so let's see here. It says set the derivative. Here's where we are. We already know that the endpoints are 0 and 6. So that's 2 of our candidates, 0 and 6. And now we want the critical value, so we're going to set the derivative equal to 0. What's the derivative? Well, the derivative is f prime of x, which is 3x squared minus 18x plus 17. So that's the derivative. We applied the power rule. Pretty simple there. And now what I'm going to do is I'm going to say equals 0. I'm setting the derivative equal to 0. And now I want to know what x values the derivative is equal to 0. So I'm going to go into the graphing calculator. I'm going to hit y equals, and I'm going to type in the derivative. 3x squared minus 18x plus 17. Now, you should already know how to do this. If you're one of my students, you've already learned how to do this. But if you don't know how to find the zeros in a graphing calculator, then you're probably going to have to either learn that, or here's the good news. This is a quadratic function. You could use the quadratic formula. That would be fine too. So we're going to hit graph. And so we can see there's a parabola, and it does cross over the x-axis in 2 places, so there's going to be 2 zeros. Now, but let's find out, is it happening between 0 and 6? So when I find the zeros here, if either one of these zeros, or if both of them, if neither one of them is between 0 and 6, then I'm going to forget it. I'm not going to use any zeros that are not between 0 and 6. This says identify the zeros on the interval. They have to be between 0 and 6. Any zeros that are not between 0 and 6 are left out. Okay? So let's see here. I'm going to go second, trace. I'm at the calculate menu. I'm going to choose option 2, which says 0, left bound, right bound. And it looks like I have a 0 at 1.174258. So I'm going to say so the derivative equals 0 for x equals 1.174258. Okay, that's one of them, and it's between 0 and 6, so we're good. Now I'm going to go second trace, option 2. All right, let's see here. And we got 4.825742. So the other 0 is 4.825742. All right, so we got 2 zeros, and this one is between 0 and 6, so we're good. So we finished step 1. We've identified all of our candidates. We've got 0, we've got 6, we've got 1.174258, and we've got 4.825742. Those are all of our candidates for maximum and minimum. Now, step 2 says put all x value candidates in a table. Here's what I mean by that. I like using a horizontal table. So I'll draw a horizontal line, and then I'll draw kind of a vertical line here, and I'll say x is equal to. And then I have 1, 2, 3, 4 candidates. So I want to split this up into four regions. There's 1, there's 2, there's 3, and there's 4. So I'm going to put 0 here. I like to put them in order from smallest to largest. 6 will go, so usually the endpoints are here, and then my other zeros go in the middle. So here I'm going to put 1.174258, 1.174258, and then this one, 4.825, 825, 742, I'll put here. So that's step 2. Put all x value candidates in a table. Step 3 says plug all the candidates into the original function. So we're going to plug these 4 numbers into the original f of x. And then it says put those values into the table. What I do is I normally put my f of x values in the bottom row. So now I have my x's and I have my f of x's. So I'm going to plug these 4 numbers into f of x. Now to do that, I'm going to use the graphing calculator. I'm going to go to y equals, and then I'm going to key in x cubed. I cleared out the derivative. I don't need the derivative anymore. I mean, if you did need it, you could just turn that function off, but I don't need it anymore, so I cleared it out. So I'm going to put in x to the 3rd power minus 9x squared plus 17x plus 7. And then I'm going to hit graph. And now what I'm going to use is I'm going to use trace. I'm going to trace all 4 of these numbers to get the output. So now I'm going to hit trace and I'm going to enter 0. When I enter 0, the output y is equal to 7. So f of 0 equals 7. Now I want to know what f of this number is. So I'm going to enter trace 1.174258, and I get 16.1716. 16.1716. Now I'm going to key this number in, 4.825742, and I get negative 8.1716. 1716. And now I'm going to put in 6, and I get 1. And so now the last step says the highest output is my absolute maximum. Let's see, highest number of these 4 numbers, the highest number is 16.176. So that makes this my absolute maximum. And the lowest number, the lowest output is my absolute minimum. Well, there's only one negative number, so that must be the smallest number. So this is the absolute minimum. And so now to answer the question, identify the absolute maximum and the absolute minimum values. So what I would say is this, is that there's an absolute maximum at, or sorry, I'll say absolute maximum is 16.1716 at x equals 1.174258. And then I'll say absolute minimum is this number, negative 8.1716, where? At x equals 4.825742. And so I hope you can see that making this table allows you to answer all your questions. Also, while creating this table, that table guides you in the process of identifying the absolute maximum and the absolute minimum. So I think that this procedure can really help you to be able to answer any optimization problem where you already have a function and an interval. Okay? Let's do a couple more examples. All right, here's another example. It says identify the absolute maximum and the absolute minimum value for the function g of x, which is cosine of x, on the interval from 1 to 4. Well, cosine is a continuous function, and this is the closed interval from 1 to 4, so we can apply the extreme value theorem. We are guaranteed an absolute maximum and an absolute minimum, so we're going to find them. Let's go ahead and start over here. Identify all x value candidates for maximum and minimum. Let's go ahead and start drawing our table, shall we? Let's do our table. We're going to have x is equal to, and then we're going to have g of x is equal to. So that's where I like to start. Now I know that my first value is going to be my lower endpoint, and then my highest value is going to be my highest endpoint. So I'm going to put a 1 here and a 4 all the way over here. So I'll put a 1 here, and I'll put a 4 all the way over here. So that's 2 of my candidates. Now I'm going to move on to the critical values on the interval. So I have to set my derivative equal to 0. Well, what's the derivative of cosine of x? G prime of x. Derivative of cosine is negative sine of x, and I will set that equal to 0. Now, I could do this using trigonometry because between 1 and 4, there are only a couple values that are going to make negative sign equal to 0. But if you rely a lot on the graphing calculator, it's okay to use the graphing calculator. Now, if you are somebody who wants to do it without the calculator, then you should go ahead and work on this, and I'll validate your answers in a little bit. But for now, I'm going to do it with the graphing calculator. So I'm going to go to y equals, and I'm going to key in negative sine of x. And then I'm going to hit graph. Now I'm only looking for outputs that are between 1 and 4. And so you can see the graph here. One thing that I can do is I can only look between 1 and 4, or I can change the window. If I press window here, I can go to x min and put in 1, and I can go to x max and put in 4, and then hit graph. And now it's only going to show me the graph between 1 and 4. And as you can see, it really only crosses over in one place. I'm going to squeeze this a little, or I'm going to stretch this out a little bit to get a better look at it. So I'll hit window, and I know that negative sign only goes between negative 1 and 1. So I'm going to maybe go between negative 2 and 2. Should make it a little easier to see. There's sign, and it looks like it only crosses over in one place. And it should be at pi, because pi, as we know, is approximately equal to 3.14. 3.14 is between 1 and 4, and sine of pi is equal to 0. Therefore, negative sine of pi is also equal to 0. Okay? So we know that the middle term is going to be pi, or the 0, but just in case, if you're the kind of person that relies on the graphing calculator, let's go ahead and find our 3.14 there. So we'll go second calc, choose option 2. Left bound, we'll make it maybe 2. Right bound, we'll make it 4. And press enter. Sure enough, 3.14159227, that's pi. All right, so 3, which is 3.141592. Let's leave it there. Okay? So we've got all of our candidates. We have our endpoints, and there's only 1 0 of the derivative on the interim. And so now all we have to do is, step 3, just plug those candidates, there's 3 of them, plug them into cosine. Now, I don't need to create the function because it's a lot easier in the main screen of the calculator to just type in cosine of 1. So cosine of 1 is 0.540302. Well, let's just do 0.5403. Okay. Now, pi, if I plug pi in, cosine of pi, we already know that that's negative 1. Okay? But, just in case, we'll type it in. Cosine of, and let's say you know it is 3.1415. So cosine of 3.141592, and it says negative 1. So we're good. Now we're going to key in cosine of 4, and that gives us negative 0.6536. And now, time to do our last step. It says that the highest output is the absolute maximum. We got a negative, this one's positive, only one positive, that has to be the absolute maximum. So this is the absolute maximum. We have 2 negative values. Which one is smaller? Negative 1 is smaller than negative 0.6. So this is our absolute minimum. Okay? And so what we would say is that g of x has an absolute maximum is 0.5403 at x equals 1, and then the absolute minimum is negative 1 at x equals pi, or you can say at x equals 3.141592. Okay? So there's another example of identifying the absolute maximum and minimum. Let's do another example. All right, here's another example. It says identify the absolute maximum and the absolute minimum value for h of x equals 4 to the x power on the interval from negative 1 to 2. Now I know something interesting about this function, but I'll give it away in just a little bit. But we're on a closed interval, so that's good. So we're halfway to the extreme value theorem. all exponential functions, all basic exponential functions are continuous from negative infinity to positive infinity. No asymptotes, no jumps, no holes. So that means that h of x is continuous. Therefore, we can apply the extreme value theorem. So we're going to go ahead here, identify all x value candidates. Well, we've got the endpoints. Let's grab start making our table. We're not going to need as long of a line here. So x is equal to, and then h of x is equal to down here. And our endpoints are -1 and 2. -1 and 2. Now let's see where, let's identify the critical values between -1 and 2. So we need the derivative of 4 to the x power. Well, the derivative, h prime of x, is going to be 4 to the x power times the natural log of 4. Now here's the thing. Here's what I happen to know. Natural log of 4, that's a constant. The only variable in here is the exponent on 4. And exponential functions, unless they have a modifier, unless they have a plus or a minus, they never equal 0. So if we say this equals 0, it actually can't equal 0, and we're going to put it in the calculator just to prove it. So I'm going to put 4 to the x power times natural log of 4. There it is. Now we're going to hit graph, and you're going to see, whoops, look at that. I need to move it back to the normal screen. I got to hit zoom and then 6, zoom standard. Okay, and now you can see, we're looking at this graph, it does not cross over the x-axis. It's hard to see down here, but if we change the window to make the y min, make it like negative, I don't know, 0.1 up to 0.1, so that's really small. You'll see that it's not going to cross over. It's not crossing over the x-axis at all. So there are no zeros to the derivative. And so for this entire problem, we don't have any critical values. We only have the endpoints. That is all, just the endpoints. So we can plug -1 into the original function. 4 to the -1 power is 1/4. And then 4 to the second power, that's 4 squared, that's 16. And so our smallest value is 1/4. That's our absolute minimum. And our largest value is 16. That is our absolute maximum. And therefore, we can say that h of x has an absolute maximum is 16 at x equals 2. And the absolute minimum is 1/4 or 0.25 at x equals -1. Okay? That was an easy one. Just so you're aware, we can do all different kinds of functions. We can do absolute maximums and absolute minimums. Let's try another problem. All right, so here's another one. We're back to a polynomial. We're looking for the absolute maximum, absolute minimum on k of x, which is a cubic polynomial on the closed interval from -4 to 4. Why don't you pause the video and see if you can do this one on your own, and then watch me work it out. Okay, so we need candidates. We need x values that we're going to put in the top of the table. So our x values in the table, and then on the bottom we'll have our k of x values. So we're just setting up a table here. And we know that -4 is going to be one of them, and we know that 4 is going to be the other one. So now, to find the critical values, we need to find the derivative and set it equal to 0. So k prime of x is going to be -3x squared plus 2x plus 10. This is a quadratic, so you could use the quadratic formula to find the zeros if there are any zeros. Because it is quadratic, there can only be up to 2 zeros, and they may not be on the interval from -4 to 4. I'm going to use a graphing calculator. So I'm going to hit y equals. I'm going to clear out y1, and I'm going to put in -3x squared. I'm going to put plus 2x, then I'll put plus 10, and I'm going to hit graph. I just realized I didn't reset my range here, so I'm going to hit zoom 6. And there's our derivative right there. It's a nice parabola upside down, and it looks like both zeros are between -4 and 4, so we're going to have 2 critical values. So when the derivative is set equal to 0, let's see here, we'll put this here, and this here. So we'll put one here and one here. So I'll go second trace, option 2. One of them looks like it's between maybe -3 and 0. And I got -1.522588. -1.522588. So that's one of my critical values, one of the zeros of my derivative. Second one, we'll go second calc, option 2. Looks like it's between 0 and 3. Looks like I've got 2.189 255. 255 or 254. All right, there's my critical values. So I've identified all of my candidates, my endpoints, and my critical values. Now I need to, and I put them in a table. Step 3, I'm going to plug all 4 of these numbers into the original function, -x to the third power, etc. I would like to use the, you know what I'm going to do? I'm going to use the table feature. I'm going to go to y equals. I'm going to clear out y1. I'm going to key in the function there, -x to the third power. Then I'll put plus x squared. And then I'll put plus 10x minus 2. And then what I'm going to do is I am going to go to second window, which will give me table set. And then I'm going to go down here to independent ask. Then I'm see graph right there. It says table above it. I'm going to hit second graph. It gives me a table. And now I can just key the numbers in. So I'm going to key in -4. See that? -4. Press enter and it gives me the output, 38. So when I key in -4, I get a 38. Now I'm going to key in -1.522588 and press enter, and I get -11.38. Now I can get a better decimal if I highlight it. If I go up and over, it says -11.3778. -11.3778. Now I'm going to key in 2.189255. 2.189255. Oops. I need to come, see this right here? It's still highlighted. I need to come off of there and go down to where it's blank. Now I can key in 2.189255. Press enter. And the output is 14.193 or 14.1926. 14.1926. And now I'm going to key in just 4. So I go over here, down here, to where it's not highlighted, or where there's nothing highlighted. Hit 4, press enter, and it's -10. -10. And so now I have 4 output values, and I have to decide which one is the highest output and which one is the lowest output. Well, of these 4 numbers, it looks to me like the highest number is 38. So that means this is the absolute maximum. And the smallest number, even though these two are really close, -10 is not quite as small as -11. So here is my absolute minimum. And so I'm going to answer the question. I'm going to say that this function has an absolute maximum is 38 at x equals -4. It's one of the endpoints. Then the absolute minimum is -11.3778 at x equals -1.5225. That's good enough. And that is the answer to this. Hopefully that's what you got when you paused the video and you tried it yourself. Let's try a couple more examples. All right, for this example, we've got a quadratic. So this one's kind of easy, but we have an issue here. Do you see our interval? So you've got x squared plus 6x minus 3, but on the interval from -5 to 1, where we're including -5, but we are not including 1. It's the interval is open on the other end point. Okay, so here's the thing. We cannot guarantee that we'll have a maximum and minimum. We can still do the problem. We can still try and identify the maximum and minimum, and we're still going to do it the same way. But here's the thing. If, when we get to the very end down here, if either the highest or the lowest point includes 1, if 1 is the answer for highest or lowest point, then we're just not going to include that. But if our absolute maximum and minimum are not 1, if it's -5 or one of the critical values in between, then we're okay. All right, so we're going to go ahead and proceed normally. Do you want to pause and try it? Do that right now. Okay, so hopefully you have a table in front of you, you have a decision, you've identified all your candidates and your outputs. Now let's confirm, okay? I don't think I'm going to need a calculator for this one. I'm going to create my table. I'm going to find my candidates. So I'll say x is equal to, and then I'll say p of x is equal to. Now my endpoints are -5 and 1. You might say, well, Mr. Ryan, why are you including 1 if it's an open interval? The reason I'm including 1 is because I need to know if there's a maximum or minimum point at 1 so that I can exclude it and not accidentally call one of my other points a minimum or a maximum. Okay, so I have to include 1 temporarily just in case that's where one of the maximums and minimums are. So we're going to include 1. Now to find the critical values, we need the derivative of p of x. So p prime of x is going to be 2x plus 6. If we set that equal to 0, we'll subtract 6 from both sides, and we'll get 2x equals -6, and x is equal to -3. And since -3 is between -5 and 1, we are going to include it as a candidate. And these are all of our candidates, the only critical value and the endpoints. So now we're going to plug these 3 numbers into our quadratic here. Well, -5 squared is 25. -5 times 6 is -30, and then -3. So we got 25 minus 30 minus 3. 25 minus 30, that's -5. -5 minus 3, that's -8. So the output value, P of -5, is -8. All right, now let's plug in -3. -3 times -3 is 9. -3 times 6 is -18. And so 9 minus 18, that's -9. Minus 3 is -12. So -12 is our output. Now we'll plug 1 in. Okay, so we plug 1 in. 1 squared is 1. 6 times 1 is 6, so that's plus 6, minus 3. 1 plus 6 is 7, minus 3 is 4. And so this is what I'm talking about here. Now we're at the point where we have to choose our highest and our lowest point for our maximum and minimum. Our lowest point is -12. So that means we have an absolute minimum at x equals -3, and that absolute minimum is -12. That's the lowest point. It's the parabola, right? It's the vertex of the parabola. But the highest point, the largest value here, is 4, meaning that the absolute maximum is would be at 1, 4, but because 1 is not included on the interval, that means that this function has no absolute maximum. This function has no absolute maximum at all. And so what we're going to say is that there's an absolute minimum of, absolute minimum is -12 at x equals -3. And then there's no absolute maximum. Okay? And that's okay, because the extreme value theorem doesn't apply in this particular case. Let's try another example. All right, here's another example. It says identify the absolute maximum and the absolute minimum value for q of x, which is e to the cosine of x, on the interval from 1 to 5. 5 is included, 1 is not. Because we do not have a closed interval, we cannot guarantee an absolute maximum and an absolute minimum on this interval. Okay? But that doesn't mean that we can't look for one of them or both of them anyway. We'll still follow our procedure, and if the absolute maximum or the absolute minimum comes out to be where x is equal to 1, we will simply ignore that particular maximum or minimum. All right, so we need the endpoints. We've got to identify all of our candidates. So our x values for candidates, we'll start with, and then we'll put q of x on the bottom here. Our candidates are 1 and 5, 1 and 5. And then we'll see if there are any critical values on the interim. To find those critical values, we need the derivative of q of x. Now, note that this is e to the power of cosine of x. which is going to require the chain rule because this is a composition function. We have a function inside of another function. So the derivative of q, so q prime of x is going to be derivative of the inside. Well, what's the derivative of cosine? Well, it's negative sine of x times the derivative of the outside. What's the derivative of e? It's e. I mean, it's not just e, it's e to the x, right? The derivative of e to the x is e to the x. So that's what we're putting, e to the x. But instead of putting x, we're going to put that inside function, we're going to leave that alone. So it's e to the cosine of x, okay? So here is our derivative. Now, I think that I am going, even though I could do this with trigonometry, I could do this with the unit circle, I'm going to go ahead and use a graphing calculator. So I'm going to grab a graphing calculator here. I'm going to go to y equals, clear out my function, and I'm going to key in negative sine of x times e to the power of cosine of x. And then I'm going to hit, I'm only going from 1 to 5, so I'm going to hit zoom 6. I'm going to get my regular graph. Let's see what it looks like. We got a few zeros there. Let's see if there are any between 1 and 5. It looks like there might be 1 or 2 between 1 and 5. I think I want to zoom in there. So what I'm going to do is I'm going to hit window, and I'm going to go x min is 1, x max is 5. See, what I do is I put the interval there, 1 and 5. I put that in my x min and my x max, so then when I graph it, it only shows me the graph between there, and then I can focus only on those zeros. And it looks to me like there is 1 0 right there. Now I can clear this up if I go back to window and change my y min, my lower and my upper, to from maybe -4 up to +4. It should look a little bit clearer. There it is. It is coming a little bit clearer. And it looks like indeed it is crossing over in only one place. So we're going to find out what 0 that is. So we'll hit second trace, option 2, and we'll go left bound. I'm just going to arrow left to make sure I'm on the left side of the 0. Press enter. Then I'm going to arrow right. Make sure that I am on the right side of the 0. Keep going, keep going, keep going, keep going. All right. Press enter. Then guess. It says that there's a 0 at 3.141592. That's pi. All right. So we're going to put pi. Or if you wanted to, since you may not recognize it, you can just put in 3.141592. So there we go. We have got our critical value and we've got our 2 endpoints. Now we're going to plug these values into the original function and find our output values. So let's go back to, I'm going to go to the main screen and I'm going to do it that way. I'm just going to key in e to the power of cosine of 1. So e to the power of cosine of 1. And I get 1.7165. 1.7165. Now I'm going to key in pi. Now I actually know what it is. If I put pi in here, cosine of pi is -1, right? So this is going to be e to the -1 power, which is basically 1 over e. Now, this isn't going to help you, though, because if you don't know what 1 over e is, then you're not going to be able to compare it to the other numbers, which is why it's probably better to go ahead and key pi in here or key in 3.1415 and get a decimal value. So we'll go second e to the power of cosine of 3.141592. And we get 0.3678. 0.3678. That's truncated. If you rounded, it would be 79. Now we're going to key in 5. So we're going to go e to the power of cosine of 5, and we get 1.3279. And so now we're going to say, which one is the largest value? Well, here's the largest value. 1.71 is larger than 1.32. So here's our absolute maximum. Now, what you may be thinking, I know what you're thinking, because we're now going to say no. We're now going to say that this is not the absolute maximum because 1 is not included. Now, this is our absolute minimum. Our lowest value is 0.3678. So here's our absolute minimum. And what you're thinking is this. I know what you're thinking, or someone out there is thinking this. If we're going to ignore this one, if we're going to eliminate this one, then shouldn't we then just say that this one is our absolute maximum? And the answer is no, because leading up to this 1.7165, because of the intermediate value theorem, other values larger than 1.32 are being approached as this function goes away from 1. For example, if I put in 1.001, if I do e to the power of cosine of 1.001, which is included on this interval, I get 1.715, which is still larger than this. So we cannot say that this is the absolute maximum. What we are going to say is that there is no absolute maximum at all for this function on that interval. There is only an absolute minimum. That is the procedure. You don't simply switch the absolute maximum. You say there is no absolute maximum at all. Okay? So we're going to say that there is no absolute maximum, and we are going to say that there is an absolute minimum is 0.3678 at x equals pi, or you can say at x equals 3.141592. Okay? And that's this question. We're going to do one more example. I think you will have this pretty good. All right, this is our last example. Got good news. We got a closed interval here. This function right here, x squared, is continuous. Sine of x, also continuous. When you multiply two continuous functions, that results in a continuous function. So that means that t of x is continuous from negative infinity to positive infinity, and definitely continuous on the closed interval from -2 to 6. So we can apply the extreme value theorem here. We are definitely going to find an absolute maximum and an absolute minimum. So let's start with our endpoints. Let's make our table. We have x equals, and we'll put our output values for t of x down here. And our endpoints are -2 and 6. So that's a good start. Now let's identify our critical values. We need the derivative of this function right here. We need t prime of x. Now, this is a product of two functions. So therefore, we need to apply the product rule. Okay? So derivative of the first is 2x times the second, sine of x, plus the first, x squared, times the derivative of the second, derivative sine is cosine of x, and so there is our derivative. We are going to set this equal to 0, and we are going to use a graphing calculator to identify the zeros of the derivative. So I'm going to go to y equals, I'm going to key in 2x sine of x plus x squared times cosine of x. Then I'm going to hit zoom 6 because I want to go back to the original frame of the graphing calculator. And there's a crazy looking function there. All right, looking pretty crazy. Now, I'm looking for all of the zeros that only go between -2 and 6. So I'm going to hit window, and for x min, I'm going to key in -2, and for x max, I'm going to put in 6. Then I'm going to hit graph again. Now it's only going to show me the zeros that run between -2 and 6. And it looks to me like there are 2 of them. It looks like, see right there at 0, it really looks like it hits the x-axis when x is equal to 0. And then it crosses over here and here, so it looks like 3 critical values. Let's confirm. I'm going to hit trace, and then I'm going to enter x equals 0, enter, and sure enough, when x is equal to 0, y is also equal to 0. And this is the derivative. This is the derivative. So we have an output of 0 when x is 0. So one of our critical values is 0. And now we have 2 more critical values. So a total of 5 critical values. Now we need to find this one right here, and we need to find this one right here. So 2 more zeros. So we go second calc, option 2. The first one looks like it's between maybe 2 and 3. Left bound 2, right bound 3, enter. And sure enough, 2.288929. So 2.288929. 0.8929. Now the second one looks like it's between 4 and 6. So second calc, option 2, left bound 4, right bound 6. And let's see here. Yeah, sure enough, 5.086, 5.086, 985, 985. All right, so we have 3 critical values, 2 endpoints for a total of 5 candidates. We're going to plug all 5 of these into that function. I'm going to use the table feature like I did before. So I'm going to go to y equals. I'm going to clear out the derivative, and I am going to key in x squared sine of x. X squared sine of x. There's my function. Now I'm going to hit second window to get table set, and I'm going to make sure that it says ask right there. Then I'm going to hit second graph, and it's going to give me this table feature. And I can just put new numbers in here, and then these will go away. So I'm just going to key in all my numbers and look at my outputs. I'm going to key in -2, enter. I'm going to key in 0, enter. I'm going to key in 2.288929, enter. I'm going to key in 5.086, 985, enter. And then I'm going to key in 6, enter. And here's all my output values. You can see them. I'm going to have to go highlight them like this to get their more precise value. But you can see when I plug in -2, it's -3.6371, or 72 if I round. When I plug in 0, I get 0 again. When I plug in 2.2889, I get 3.9453. Then 5.087 gives me 24.0829, or maybe 24.083. And then when I key in 6, I get -10.059, I guess. Okay, so let me write those in. -3.6371, or 6372. When I plug in 0, I get 0. When I plug in 2.288929, I get 3.9453. 3.9493, or 53, sorry about that, 53. Yeehaw, 53. Now, when I key this next one in, I get -24.083. And then when I plug in 6, I get 10.059. 10.059. And now I just need to identify the absolute maximum and the absolute minimum. It looks to me like the largest value of all these is this over here. That's the largest. And the smallest value to me looks like this one right here. So this x value and this output value, this is my absolute minimum, and this is my absolute maximum. And so I'll say that there is an absolute maximum is 10.059 at x equals 6. That's an endpoint. Then the absolute minimum is -24.083 whenever x is 5.087, I guess. 087. There we go. All right. Well, that's your first lesson in optimization. If you are able to do this, you are in really good shape, because when we get to optimization 2 in the next class, you'll be able to just apply this after the new stuff that you learn. Okay?